Here we have a question 2 that says a heavy object is lifted using 2 ropes and 2 pulleys, as shown in the diagram below. The 2 pulleys are at distance x apart. The force Fa in rope A is 730 newtons, and the force Fb in rope B is 1440 newtons. Rope A makes an angle of 70 degrees with the horizontal, and rope B makes an angle of 10 degrees with the vertical. So this is the system that we're working with. And immediately we notice that we have tension at an angle. So we know that whenever we're working with forces at an angle, they have to be broken up into components. Now, we'll break them up into components later on when we need to do calculations, but for now, we know that the center point, or the main point that is going to experience the 3 forces, is the object. Now, just to start off by drawing the forces that are acting on this object so that we understand what we're working with. This object is going to have some mass to it, which isn't actually given to us. So maybe we don't need that for calculation since it's not given. But we know that gravity will act downward, so it's going to pull the object down. That is known as weight or force of gravity. Then we've got these tensions Fa and Fb, and I just extended those arrows as they've been given. I'm not going to reassign names to them since they've already been called Fa and Fb. Now for 2.1, we need to define the term resultant. We have done this in previous papers, so I'm just going to mention it here, but going forward I can mention it, but I'm not going to write it down. So we know that resultant vector is a single vector having the same effect as 2 or more vectors added together. 2.2 says, explain why the vector diagram of force Fa, force Fb, and the weight will not be a closed vector diagram. Now, in the previous papers, 3 papers that we've covered, we know that a closed vector diagram is when the system is in equilibrium. Now, what does equilibrium mean? It means that the net force acting on the system is 0. So the system is actually stationary. There is no acceleration. However, when we read the information here, it says a heavy object is lifted, meaning that this object is being lifted up. So there is actually some acceleration to it since the object is moving up. So the net force acting on this object is not 0. And that is actually good enough to write as your reason. You can say that the net force acting on the object is not 0. You can say that the system is not in equilibrium. I would actually state both since it is 2 marks. Okay, so I'm going to say, here we have it, the net force acting on the system is not 0 as the system is not in equilibrium. Now for 2.3, we're going on to calculations. The first thing they want is the vertical component of Fa and then the horizontal component of Fa. Now, where we have Fa, let's just split that up into its components. So I've just adjusted those arrows so they align better with the diagram, so it's easier to understand the components. So here we've got Fax acting to the left and Fay acting up. Now remember, we said that when it comes to using theta, you need theta to be according to the butterfly diagram. So this forms the triangle that would be in the second quadrant. So here's our butterfly diagram, and we can see this is now second quadrant. So the angle that we need has to be this angle here, which we are given the correct angle. So we can go ahead and use 70 degrees. So for 2.3.1, we need the vertical component, which is Fay. That's going to be equal to Fa sine theta. So Fa was given as 730 degrees, or 30 newtons, 730 newtons, and the angle was 70 degrees. Okay, let's calculate this and see what we get. So I get 685. It's 975, but it becomes 98 when we round off. And remember, your unit is newtons. Okay, so they asked us for the vertical component. They did not say magnitude, which means that we need direction as well. We notice that this component goes upwards. So you can say up, upwards, north if you're using compass directions. And then 2.3.2, we need the horizontal component. So horizontal component is going to be FAX, and your formula is FA cos theta. So FA was 730 newtons, theta was 70 degrees. So here we get 249.67 newtons. And just referring back to the diagram so that we can get direction, FAX pointed to the left, or it would be west if you're using compass directions. Two 2.4 says calculate the maximum weight that force FA and force FB will be able to lift from the ground. Show all calculations. Now here's the thing. The maximum weight that these two forces will be able to lift from the ground. In other words, they are asking you, what is the weight of this object? But when we think of the maximum weight that these forces are going to lift off the ground, we need to think about the system being in equilibrium. Because the maximum weight would be experienced when the object is stationary. So when those ropes are forced to hold up the stationary object. So we can calculate this, yes, using Newton's second law, where F net is equal to ma, but in the sense that we are going to solve for W, but treat the system here as if it is in equilibrium, so that we can calculate the maximum weight. So we can say F net in the y direction is equal to ma or is equal to 0. And what are all of the forces acting in the y direction? Now clearly we see that we have Fay, but what about Fb? Fb will also have to be broken up into components. So here's your components for Fb. Fby is going to act upwards. Fbx is going to act to the right. However, the angle that you're going to use for theta, if you form a triangle here, that matches the triangle in the first quadrant, which means the angle that you need to use needs to be this angle. Since the quadrant is 90 degrees, you can subtract 10, so the angle that we're using as theta here is 80 degrees. So that's actually when we need to calculate Fby. But for now, since we are expanding F net in the y direction, we are going to have Fay acting up, Fby acting up, and Fg acting downwards. So what we'll be solving here, or solving for here, is Fg. So there's our expansion. And we can actually further expand because we do have the value for Fay, but we haven't calculated Fby. So I'm just going to expand that. It would be Fb sine theta. We're not going to expand Fg because we actually need to calculate the total weight that it can lift up, which is represented by Fg. So let's take Fg over to the right. Now let's substitute everything that we have and solve for Fg. So Fay, our value was 685.98. For Fb, if we refer back to the diagram, Fb was 1440 and theta was 80 degrees. That is equal to Fg. So let's put this on our calculator to see the maximum weight that these ropes can lift up. So here's what I get, 2104.10 newtons. So that is the maximum weight that force Fa and Fb can lift up. 2.5 says, explain why the rope and the pulley system will be less effective if the distance x between the pulleys is increased. Now, referring to the diagram, here we have the distance x. And we want to understand what's going to happen if this distance is increased. So I'm just going to draw that arrow a bit longer so we can visualize what takes place. So imagine that this distance x now increases to the blue arrow that I've drawn. What's going to happen there is it causes the force Fa to now act upon this point. So these circles that we have, right, these pulleys, they are now going to move as well. And it causes Fb to act at that point, essentially decreasing these angles. It'll no longer be 70 degrees, neither would it be 80 degrees here. What happens when these angles are going to decrease? The y components are going to decrease as well. So since the y components of the forces decrease when the distance x is increased, remember your y components are acting up. They are responsible for lifting up the object. So if they are going to decrease, they cannot lift up such a big weight. So they can no longer lift up such a big weight, which means that they'll still be able to lift up some weight, but not the maximum weight that we calculated. So they wanted us to explain why the system will be less effective. So yes, we know that if this distance x increases, the vertical components of these forces will decrease. And this system could possibly not be able to even pick up the weight. So yes, it will be able to pick up something, but not necessarily this object that we have. So here's how we can word this answer. If the distance x increases, the vertical component, or let's say components, of the forces Fa and Fb will decrease. Therefore, the system might not be able to lift up the weight. So yes, we know that the system is going to be less effective than it was before. Please remember to like, subscribe, and turn on your notifications for more content.